Okay, class, we are going to talk about section 3.5 in this video. We're going to review some limits, but in this section we're going to talk about limits at infinity. So all of the problems are going to be as x approaches infinity. So our first problem, the limit as x approaches infinity of 2x minus 1 over x plus 1. If I plug infinity in for x, I will get infinity over infinity. Infinity over infinity is an indeterminate form. Which means that we can do something with it to make it determinable and then find the limit. I'm going to talk about a couple different things. The first thing is going to be really what we are looking for as x approaches infinity and what kind of graph this is. So if we are just looking at y equals 2x minus 1 over x plus 1, hopefully everybody knows that this is a rational expression. We have a 0 at 1/2, we have a vertical asymptote at -1, and we have a horizontal asymptote at 2. So how did I know all of that? Well, if I set 2x minus 1 equal to 0, x equals 1/2, and that's our 0, because that's where the numerator would be 0. If I set the denominator equal to 0, I get x equals -1, and that is our vertical asymptote. And then for our horizontal asymptotes, we look at the degrees. So in this case, both of them are degree 1. So you take leading coefficient divided by leading coefficient. So to find horizontal asymptotes, you're going to have 3 different cases. The first one is if the degree of the numerator is equal to the degree of the denominator, then you take leading coefficient, so y equals will be leading coefficient divided by leading coefficient of the denominator. And whatever that value is, will be the horizontal asymptote. The second case is going to be if the degree of the numerator is greater than the degree of the denominator. And in that case, we do not have a horizontal asymptote at all. We have some kind of slanted something, either a line, depending on what it is when it divides out. So in this case, the limit will always be infinity. Up here, in case number 1, the limit is always going to be the horizontal asymptote. And then the third case scenario is if the degree of the numerator is less than the degree of the denominator. And if that is the case, then our horizontal asymptote is always y equals 0. Okay, so in this case, we do have a horizontal asymptote of 2, if this is our equation here. So if we look at the graph, we know that no matter if the graph, where the graph is, it's always going to approach this horizontal asymptote as x goes to infinity and as x goes to negative infinity. Now, because I have this 0 right here, I pretty much know what my graph is going to look like. So as this graph goes to infinity, as x goes to infinity, my graph is always going to approach 2. And it doesn't matter if it's infinity from the right or to negative infinity, it's always going to approach 2. So, because our horizontal asymptote is 2, our limit is going to be 2. So let's look at a couple more examples. The limit is x approaches infinity of 2x plus 5 over 3x squared plus 1. Again, I'm going to get infinity over infinity. So that means I'm looking for the horizontal asymptote. The degree of the top is less than the degree of the bottom, so my limit is going to be 0 because my horizontal asymptote is 0. If I just change the problem just a little bit, I'm going to add a square to my numerator, then that means the degrees are the same, and I am going to approach the horizontal asymptote, which in that case is 2/3. And then the last case scenario will be if I have 2x cubed plus 5 over 3x squared plus 1, which means my horizontal asymptote is not horizontal at all. It's oblique. It is going to be a line, but it's going to go to infinity. So the limit is going to be infinity. You can also put does not exist because if the limit is infinity, then it doesn't make sense to go to infinity and have a limit. A couple other problems that you're going to run into is if there's a radical in your limit. So the limit is x goes to infinity of 3x minus 2 over the square root of 2x squared plus 1. So in that case, it may look like the degree of the top is less than the degree of the bottom, but it really is not, because we're just looking at the first terms. So the degrees are the same. So in this case, our horizontal asymptotes are plus and minus the square root, or 3 over the square root of 2. So as we go to infinity, we're going to approach that positive horizontal asymptote. So my answer will be positive 3 over the square root of 2. As I go to negative infinity, it will approach the negative horizontal asymptote. Now, if I change my function a little bit and it's negative, a negative term, then you might have to do a little bit more investigation to decide which one of those asymptotes it's approaching. So let's just take a look at this one. Just move that over. Let's say I'm going to type this in as 3x minus 2, and you can graph this as well, divided by the square root of 2x squared plus 1. I'm going to make my window a little bit larger. Okay, so you can see the horizontal asymptotes. I can even type in the equations of the horizontal asymptotes. So for one equation, I could type 3 divided by the square root of 2. And then for the next one, I could take negative 3 divided by the square root of 2. So we can see those asymptotes written as equations. And you can see how the graph is approaching those. It does cross one of them. Okay? So that is how you do solve these algebraically. You just look for the horizontal asymptotes. Hopefully some of you remember L'Hopital's rule. You may apply L'Hopital's rule to these limits if you want to. I feel like it probably takes more time to do it that way, but you are more than welcome to if that's how you want to solve the problem. Okay, for homework, I'd like for you to do in section 3.5 of your books. I want you to do just a couple problems to see if you get them correctly. I'd like for you to do numbers 17 and 19. 17 and 19. It's page 205 if you have the hard copy of your book.